Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.2.9. Um, More on the generalized Pythagorean theorem. All right, let's look at an example. Let's suppose that we have two vectors written as columns and put into a matrix. And we know that we can find the area of the parallelogram between these by considering the different two by two submatrices that we have here and looking at the determinants, squaring them because the determinants are just the projections onto the different planes, and then squaring those projections and square rooting it. Okay, and that would give us the area of the parallelogram. All right, let's look at something we can do. What if we take the transpose of this matrix, meaning we switch, we make the columns rows, and so the first column here became the first row here, second column becomes the second row here, and we multiply this out, we get a square matrix. And notice that the determinant of this is 57, which is the square of the actual area. So kind of an idea is this kind of generalized Pythagorean theorem in some sense, if you want. Instead of thinking about this sum of squares, you can actually just think about taking the transpose of this matrix, multiplying it, and then taking the square root of the determinant, and it'll work the same way. One major reason is because so we can get this sum. This idea comes from a proof, as well as some other ideas which are hinted at in the previous subsection, which I'm not going to go through. It's optional, but you can look at it if you want, and it might give you some ideas where you can point you to other places to look. Okay, but let's take a look, and why don't we just look at this example, a single vector AB, and now we're finding the length of this because one-dimensional area is just length. So finding the length of this, using that idea, we take the transpose of it, AB, and the vector itself, we multiply these, and notice that the multiplication of these is simply a squared plus b squared, and the determinant just a constant, and the determinant of a 1-by-1 matrix is just the constant itself. And so we actually get the Pythagorean theorem out of this very nicely. The same thing could be done if we were finding the length of a single vector that was like ABC, like up and down. Same thing would apply. The area of a parallelogram in space, here's another example. Again, we have a square matrix. We find its determinant. Okay, that concludes this little subsection. Thanks for watching.